Hello and welcome to Team VLSI. Today we are going to discuss about OCV, AOCV and POCV, that is on-chip variation, advanced on-chip variation and parametric on-chip variation. We are discussing this session under the series various issues in the physical design. So please do like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can search Team VLSI on Google. We have also a blog, teamvlsi.blogspot.com. So you can visit there and check. There are many articles there on different topics. So let's begin this topic. Highlights. First we will see the highlights of this session. So highlights are, first we will discuss about the OCV, then issues with OCV and need of AOCV. Then we will move to the introduction of AOCV, then issue with AOCV and need of POCV. Then we will discuss introduction of POCV and comparison between AOCV and POCV. So let's start the first section, that is introduction of OCV. We have already discussed the OCV in the previous session of this series. So I will provide the link of that session in description. That session is very important before understand this session. At that session we have discussed the sources of on-chip variation and their nature. So it is important to know the sources of on-chip variation and their nature. I would suggest to watch that video tutorial to understand the process variation in details. In this session briefly we will discuss about the OCV, and there are two types of process variation. First is systematic variation and second is random variations. So in systematic variation, it is predictable in nature and could be modeled and tuned the process as the technology node gets matured. But random variation is highly unpredictable in nature. So it is difficult to model about the random variations. So these variations could result change in delay of cells and nets, and further could failure the setup and timing of the design, setup and hold timing of the design. So ultimately the variations, these are the variation related to your fabrication methods and the technique used in your fabrication, equipment used in fabrication. For different type of variation could occur there, and it can vary your delay of cells or nets that ultimately will affect the timing of your design. To make the design immune of these delay variations caused by the fabrication process, we have to perform static timing analysis with consideration of such process variation. So thing is, while doing the static timing analysis of your design, we have to consider that such type of variation may occur while in the fabrication, and corresponding delay we have to predict and add while doing the static timing analysis. Okay, so in OCV, a fixed timing derate factor is applied globally to all the cells or nets of the design during FTA. If any process variations occur and cell delay changes within the predicted limit used in the derate, it will not violate the timing of design. In this way we consider our variations while doing the FTA. So fabrication process variations could either increase or decrease the delay of cell. So we need to set late and early timing derate factor. So either it can make your delay worse, or it can make the delay early, means your cell can could be fast also. So here is an example of setting the derates in OCV. Set timing derate, then cell delay. We can set the cell delay or net delay here. So syntax is set timing derate. Then we have to mention the cell delay or net delay. Then we have to mention either rise or fall delay. Then is it data path or clock path? Then we have to mention early or late. So for example, in the first it is the delay is early by 8%, and in second example it is delay by our rise time is increased by 10% of the nominal delay. In setup and hold timing analysis, there could be different scenario. For the setup analysis, here clock is coming, this is the launch flop and this is the clock flop, and clock is coming from the clock pin to the launch flop, and it also goes to the capture flop. So the path from the clock pin to the launch flop is called launch clock path, and the path between the launch flop and the clock flop through the combinational cells is called your data path, and the path starting from the clock pin to your capture flop is called capture clock path. Similar in the your hold analysis. In setup analysis, how your timing could be failure due to your on-chip variation. So thing is, if the data will reach in capture flop late, then only your setup can violate. So how that can happen? That could be happen by if your this path means data path is slow, or your launch clock path is the late, or your capture clock path is early. For the data path, we will consider the late scenario, and launch clock path we will also consider the late arrival, and for the capture clock path we will consider the early arrival. That's the worst case, and we have to consider the worst case for taking care of the setup analysis, so that setup could not so that setup is not violate. So for setup timing analysis, STA tool will consider worst scenario, and so late timing derate will be considered for the data path and the launch clock path, and early timing derate will be considered for the capture clock path. And in similar way, for hold timing analysis, early timing derate will be considered for the data and launch clock path, and late timing derate will be considered for the capture clock path. Okay. So next is our issues with OCV and need of AOCV. AOCV is advanced on-chip variation. So here is a path delay of OCV fixed rate. So your green line is a nominal delay, and in x-axis we have stages. So here we have 6 stages: stage 1, stage 2, stage 3, stage 4, stage 5, and stage 6. So every stage we have 20 picoseconds delay. So up to stage 6, nominal delay is 120, and red line is showing your late derate, which is our here we have considered 20%. So in every stage we added 20% of late delay. Like it's after stage 5, nominal delay is 100 picosecond, but late delay will could come up to 120 picosecond, and early delay it could be it could be 80 picosecond. Okay, similar at stage 6, 120 picosecond is normal delay, 144 picosecond is your late delay, and 96 picosecond is your early delay. So there is a variation from 96 to 144, and that is 48 picoseconds variation. 24 picosecond in either side. So the fixed timing derate used in OCV is over pessimistic. Why over pessimistic? Because consider there are 6 stages, but it is not necessary that every stage simultaneously will late or simultaneously will early. It's random. So in some stage it could be either late or early. In reality, random variation is less for higher path depth because not all the cells in the path simultaneously become late or early. So delay cancellation is there. So suppose 1 or 2 stages become early and rest are the lates, then definitely our the worst delay won't be 144 ps. So this fixed derate model of OCV is oft pessimistic. So delay cancellation is there, which is not taken care in fixed derate of OCV. So in OCV we are not considering such the delay cancellation things. So the concept of fixed derate application was modeled in technology node above 90 nanometer, but in lower technology node and higher frequency design, the timing closure becomes very difficult due to the over pessimism of fixed derate. We need to overcome this pessimism. So the concept of advanced on-chip variation AOCV has evolved. AOCV has introduced below 65 nanometer technology node to model the variation in a better way than the fixed derate OCV. In AOCV, fixed derate is not used, and we have different concept there to take care of process variation. So let's see the introduction of AOCV. So in AOCV, derate is applied on cell based on the path depth and distance of the cell in the timing path, and it is also varied with cell type and drive strength of the cell. So basically you can see here the fact your derate is a function of your path depth and distance. It is no more constant like OCV. What will be the delay of a cell? It will depend the cell's path depth and distance. We will discuss these two things in details in this section, and also it is not constant for all type of cell and all type of drive strength. It varies according to the cell type and drive strength of the cell. First let's see what is the meaning of distance and how according to distance your derate factors vary. So if the distance increases, systematic variation would increase, and to mitigate the variation we need to use higher derate value. So it says that if distance increases, systematic variation will increase, and if the systematic variation is increased, we have to consider the higher derate value. Okay, so here is a launch flop and a capture flop at a timing path. So this point is called CRPR common point. Hope you understand this CRPR point in the timing path. If not, just take our overview of our internet. You will easily find what is the shear pair point. So basically it is the point where both your clocks get divided, and before that both the for the launch clock and for the capture clock the path is common. Okay, distance is calculated using the bounding box, and and upper bounding box is for your net distance, and a bounding box having the outer with the green line, this is a bounding box for your cells. So your this distance is the maximum distance for the cell, and this distance is the maximum distance for your nets. Okay, so next is our path depth. So in case of distance is fixed and path depth is increases, the systematic variation would be constant, but random variation would tend to cancel each other. So thing is, if your depth is increasing, your random variation will cancel each other, and you need to use lower derate value. Therefore, within the fixed distance and increasing path depth, we need to use lower derate factor. So here is your shear pair point, and if you consider this launch cell path, its depth is 1, 2, 3, 4, 5, 6, 7. So this cell is having depth, that is capture crop is having depth is 7, and through your capture cell path its depth is 1, 2, 3 and 4 only. As we need to take the derate, it will depend upon the path depth. Next is cell type. The derate is based on the cell type, as an AND gate and an OR gate cannot exhibit the same variation. Similarly, it varies with the drive strength, like AND 2x and AND 6x will have different derates. The path depth of the cell models the random variation component, while the distance of the cell models the systematic variation. So systematic variation is taken care by the distance, and random variation is taken care by the depth. Now we'll see the AOCV analysis mode. So there are two analysis modes in AOCV. One is clock only and second is clock and data. In clock only mode, AOCV is applied only the clock path. It has reduced effort and fast run time, whereas in clock and data analysis mode, AOCV is applied in full design, and it requires AOCV table for all design objects, that is including your all the cells in data path and clock path both. So it has been observed that there are huge timing violations have been fixed if we moved from fixed derate OCV to clock only AOCV mode, and it further improves if clock and data analysis mode is used during the STM. It removes the pessimism when in large extent when we use the clock and data mode analysis mode in AOCV. Here is a AOCV 2D derating table. So you can see here, this is the derating table of AOCV for a cell. This is just an example, not the exact value. In the x-axis we have depth, and in y-axis, negative y-axis, we have distance. So in this way our distance is increasing, in this way our depth is increasing. So you can see here, as we increasing the distance, our derate factors is going to increase from 1.130, that is 13%, to 1.147, 14.7%. So in this direction, as distance increases, our derate value is going to increase, and in this direction, as our depth is increasing, our derate factor is going to decrease due to cancellation, random variation is cancellation. So in short, if derate increases with the distance, derate increases with the distance and derate decreases with the path depth. So only thing you have to remember is the trend of variation of derate, and the reason, as I have explained in this, so AOCV file format supports multiple AOCV derate table. So this table either could be your 2D or 1D. In 1D table, either depth or distance is taken care. In 2D table, both depth and distance is taken care. So next is PrimeTime AOCV flow. So most popular tool of timing analysis is our PrimeTime, and here is the flow of PrimeTime, including your AOCV. So first stage is read and link the design. Second stage is back annotation of parasitics. The next stage is include coordinate for the distance based on AOCV. So for tool, it is mandatory to know the coordinates of each cell, because in distance, it is based on your distance. Your derate will be divided according to your coordinate. Next is applying the design constant, that is your next is your applying the design constant, and then read AOCV derate table. It could be either 1D or 2D table. Then enable AOCV analysis. It could enable either clock only or clock and data both. And then delay cell calculation and timing analysis will be done. Then it will generate the reports. So your flow is going in this direction, and this with this color, this is the standard prime time flow, and with this color, these three steps are additional steps for AOCV. Next, we will see the issue in AOCV and need of POCV. So what are the issues with AOCV and why we need POCV? So below 40 nanometer, AOCV2 becomes inaccurate as it cannot reduce pessimism. To address the shortcomings of AOCV, parametric on-chip variation, that is POCV, has introduced. POCV has been used to remove pessimism in 20 nanometer or below. POCV is more realistic than the AOCV and OCV. This method does not use the distance and depth based derate, and also not the fixed derate. It uses delay sigma to model the delay variation of fail. So what is the delay sigma and how it is modeled, we will see in the next section. An advantage of POCV over AOCV is that it reduces the slack pessimism between graph based and path based analysis. So again, one concept is here: graph based analysis, GBA, and path based analysis, PBA. So you need to understand these two things. I am not going to discuss in this session here, but you can easily understand what is GBA and PBA. Okay, so next is introduction of POCV. POCV as advanced variation technology provides statistical benefits without the overhead of expensive statistical STA library characterization. So in POCV, instead of applying a specific derate factor to all cell, delay cell is calculated. Cell delay is calculated based on the delay variation sigma of the shell. So in POCV it is assumed that nominal delay value of the shell follows the normal distribution curve. So here is the normal distribution curve and it is the central value, and most of the delay is your near your central value. Most of the data is near your central value. So if we consider 1 sigma, 68% of your delay variation is in this range. If you consider 2 sigma, 95% of your delay variation in this range, and if you consider 3 sigma, it's most accurate, and your 99.7% of delay variation falls in this range. Okay, so if you have difficulty to understand these normal delay functions, just go through a brief about normal standard deviation, what is the standard deviation, and how normal distribution functions, how normal distribution, what are the concept of normal distribution curve. Okay, so in next we have POCV analysis. So POCV uses the nominal delay value mu instead of using max or mean value of delay for modeling the random variation. So timing analysis is done using the normal delay value mu and delay variation sigma in following way. So timing analysis is done using nominal delay value mu and delay variation sigma in following way. First, tool takes the value of sigma from the timing library or an external file containing the POCV coefficient C. Each arc timing is then calculated statistically as the total of nominal delay and the variation. Next, the tool then calculates the delay of path by statistically combining these arc delay and check the setup and hold timing. By default, tool performs POCV analysis at 3 sigma from the mean, but other value can also be specified. More the value of standard deviation, it's more pessimistic. So we can change the value of sigma, either 2 sigma or 3 sigma. By default, tool is taking consideration of 3 sigma. So POCV input data. The input of delay variation sigma can be provided to the tool by two different formats. First is using the POCV coefficient C, an external file containing the coefficient of delay variation C for each library cell, hierarchical cell or design. There is only one value of C for each timing arc for cell, irrespective of input transition and output load. So input transition and output load is not considered here. Directly we are providing the POCV coefficient C for each cell in a file. The delay variation for the delay variation sigma would be your C multiplied by nominal delay mu. Here is an example of POCV coefficient file. It's version of this file, then OCVM type, which is here POCVM, object type library cell, and then RF type, that is rise or fall, delay type, it's for cell, and derate type, it's yearly, and object name here, and it is the coefficient 0.0693 here. Then second way of providing the delay coefficient is using the library variation format, that is LVF format. The information of POCV variation is directly provided in library itself. So here is an example. Here is an example of POCV LVF format for the cell delay. So here you can see it's the sigma type is late. And there are two index 1 and index 2, and its template is 4x4. It could be either your 6x6, 8x8 or more. Then index 1 and index 2, and based on that your here is your sigma value. So index 1 and what indicates index 1 and index 2? So typically index 1 denotes the input transition and index 2 denotes the output load. So basically it is based on the input transition and output load your sigma will be divided. If both data types are present in a design, then by default the file with POCV single coefficient, that is C, has higher precedence over the POCV slew load table in LBF format. So concept is if both the things is present, then higher precedence is for POCV coefficient C value, which we have indicated in this through C. So POCV delay calculation. So delay of cell will be nominal delay plus minus C into nominal plus minus C multiplied by nominal delay into N, where C is the POCV coefficient and N equal to number of standard cell deviations, or delay of cell is equal to nominal delay plus minus variation. This term is completely your variation. So POCV analysis flow for prime time. Now we will see how prime time flow for POCV analysis. So first you will require Verilog file library, then constant FDC file, then SPEF, that is parasitic RC, and these all will decide your variation setups. Will fit your variation setup. Read POCV input and enable POCV analysis. Then next step is timing analysis. Apply a statistical addition or subtraction and min max calculation. Then next stage it will generate n sigma corners timing reports. It will generate your path report, slack report, and stage derate report. So with this we will next discuss the comparison between AOCV and POCV. So in AOCV, random variation model through the depth based derate and systematic variation is modeled through distance based derate. In POCV, random and systematic variation model through a delay variation coefficient sigma, which is specific to each cell. In AOCV, less accurate correlation between graph based analysis and path based analysis, GBA and PBA. In POCV, more accurate correlation between GBA and PBA. In AOCV, transition variation of cell, transition variation and cell check variation not supported. In POCV, transition variation and cell check variation supported LBF format. So with this, here I am concluding this session. So thank you for watching this session. Please do like this video and subscribe our channel. Our channel is youtube.com/teamvlsi, or you can visit our Facebook page, facebook.com/teamvlsi. You can join our WhatsApp group. Description group link is in description. You can visit our the blog teamvlsi.blogspot.com, and if you have any doubt, you are most welcome in the comment section. Just we'll try to discuss the doubts in comments. So with this, I am concluding this session here. Okay, thank you for watching.